In order to understand AIM Command and AIM Command Pro, we need to understand where application systems started at. Speed and pressure spraying is one of the first efforts toward a higher quality application. Speed and pressure spraying operates under the assumption that as long as my speed and my pressure stay constant, I can expect to keep my rate, pressure, and droplet size all relatively consistent. As long as speed and pressure stayed constant, this worked well. Where we ran into issues was any time that we had to deviate from our target speed or our target pressure. Let's look at a tip chart to try and understand what's going on here. We see here a typical tip chart used for application systems that do not use any sort of blended pulse technology. We can notice a few things when we look at this tip chart. We find a tip that works for our speed and pressure. We realize that if we go up in speed or go down in speed, go up or down with pressure, or try to change our rate, we change all the variables in this equation. The need to stick to a single speed and pressure to maintain application consistency can cause some serious issues when it comes to productivity and quality. When rate controllers were introduced, they revolutionized the way that we applied. Rate controllers work by using a simple equation that is done multiple times a second anytime we are spraying. Thanks to the ability to do this calculation, rate controllers would allow operators to maintain a consistent rate within a certain speed range. This type of application is referred to as conventional spraying. If an operator traveled speeds outside of those limits, over or under application would occur and pressure would fluctuate as speed changed. In addition, as pressure increased, droplet size would decrease. As pressure decreased, droplet size would increase. This is because pressure wasn't being controlled, only rate. Let's look at another way to visualize the way a rate controller works. This equation is the heart of any rate-controlled system. Let's start by breaking it into its individual pieces. GPM, or gallons per minute, corresponds to the number on the tip. For example, an 008 tip would flow 0.8 gallons of product per minute. If we know the tip we want to use and we are looking to calculate the potential application rate, we would put in the potential flow here. More commonly, we will use this equation to be looking for a specific spray tip. When we are looking for a spray tip, we will use this in the way that it is shown here on the screen, and we will calculate to get the gallons per minute required per tip. Keep in mind this equation can be used for other things, like calculating the amount of flow per minute out of an entire boom or out of a section of the boom. So don't forget that this can be used also to use gallons per minute of product out of the machine, not just a single nozzle. Gallons per acre is pretty straightforward. GPA is going to be our desired application rate, and we can use it either as a part of this equation as it is on the screen, or we can solve for gallons per acre, and you see the rework of that equation here. If we have machines that are having trouble getting to rate when at high or low speeds, the first easiest thing to check is to make sure that the tips that we have on the machine will allow us to get to the target speed and target application rate. That's where we can use this new formulation of GPA equals. Miles per hour will be our desired travel speed in miles per hour, and width can be either the width between the nozzles or the width of the operating section. Make sure to remember that this is measured in inches in order to use the constant 5940. In this animation, rate is being held constant at 10 gallons per acre. Notice as speed increases, pressure increases, and overall droplet size decreases, making driftable fines increase. Driftable fines are small, fine spray particles that have the potential to not hit the target plants and get carried away by the wind instead. This chart also illustrates the 2-to-1 speed range of a conventional spray application. Starting speed was 8.4 miles per hour and ending at 16.8. This illustrates the biggest downfall of a rate-controlled sprayer. The ability to vary speed is twice that of a speed and pressure sprayer, but this is still a limiting factor. Blended pulse technology changed the application industry forever. This was the first application system that allowed operators to be at the correct rate, pressure, and droplet size through an extremely wide 8-to-1 speed range. Rate controllers were good when we achieved our target application speed, but speeding up to that speed and slowing down from that speed, and whether it was at the end of the field going through a waterway or any other reason to change speed, rate controllers would suffer. Blended Pulse technology, or AIM Command and AIM Command Pro, fix these potential issues with any rate-controlled sprayer. This animation will show us using a Wilger MR11008 tip with AIM Command at a rate of 10 gallons per acre that as speed increases, droplet size and driftable fines remain constant throughout the 8-to-1 speed range. We will start at 3.2 miles per hour and end at 26 while maintaining 10 gallons per acre at 60 pounds of pressure. This is the biggest selling feature of a blended pulse spray system. The ability to do a top quality consistent application from 3.2 to 26 miles per hour changed the way we apply. With a rate controller, we ran into certain spots in the field where we had to drive at a higher rate of speed to keep from over applying. No longer do we need to try and maintain a higher target speed going around obstacles or spraying along tree or fence lines to minimize over application. We can now spray to the field conditions and no longer need to spray to maintain quality application. Now we need to understand how this is done. The nozzle valves pulse at 10 times per second or 10 Hertz. This cannot be changed. However, the duty cycle can be manipulated to allow flow through the nozzle valve for longer or shorter periods of time, each 1/10 of a second. This change in the length of time product is allowed to flow through the nozzle is how rate is controlled. This shows various duty cycles and its effect on flow. With all this pulsing, why does an AIM Command show skips in the field? Every other nozzle across the boom pulses together. This is referred to as alternate or blended pulse technology and allows for 100% overlap in the spray pattern, thus eliminating skips in the field. Boom height greatly affects the overlap, however, and if the boom height is too low, the pattern will not overlap correctly and will show skips in the field. On the other hand, if the boom height is too high, either over or under application can occur depending on environmental factors such as wind, and will show skips as well. The minimum spray height for 20-inch nozzle spacing is 20 inches with 110-degree nozzles and 30 inches with 80-degree nozzles.